Once something is declared a function, and just a reminder, for something to be a function, every x value should only have one possible y value. But when something is a function, we can use function notation, which is just an algebraic way to represent functions, and it is a very efficient way of asking certain questions. So these are examples of function notation. F at x, h at t, r at x. F at x is just a general function, okay? It tells you the name, the function is f, and what it depends on, which is x in this case. For h at t, it could be something about a word problem. The function is the height, and the height depends on time. Or for r at x, r is revenue, and it depends on x, which might be the number of items being sold or manufactured or whatever it might be. So already we can see that function notation can tell you a lot about the independent and dependent variables. But like I said, it's also very efficient. So if I give you something like f at 4, I'm asking you, what is the y coordinate when x equals 4? Because f at x as a whole, or h at t as a whole, it's the y coordinate, or the dependent variable. So f at 4 means sub 4 in for x and simplify. Or I can say f at x equals 7. So I'm giving you the y coordinate, which means set your equation equal to 7 and solve for x. So two different types of questions. It's just a faster way of asking it. So let's say I give you two functions, f at x and g of x. F at x is a quadratic, g of x is a line. And I want you to evaluate first f at 3. That means, what is y when x equals 3? But that's a pain to write, so f at 3 is a lot more efficient. So all I'm going to do to evaluate f at 3 is substitute 3 in for x wherever I see it in function f. So instead of x squared, I will write 3 squared. Instead of 2x, I'll write 2 times 3, and then plus 4. Now it's a BEDMAS question. So I will simplify my exponents first. 3 squared is 9. I'll also simplify my multiplication. 2 times 3 is 6. And then the plus 4. And if I add those numbers up, I get 19. Now, this tells me when x equals 3, y equals 19. This represents the coordinate 3, 19 on your function. Let's try another one, and this time I'm asking for g at -4, which is the same thing as x is -4, what is y, but it's function g this time. So I'm going to go to my line equation, that 5x minus 7, and instead of x, I'm going to write -4, and now I simplify. 5 times -4 is -20, subtract 7, -27. And again, this represents a coordinate. X is -4, and the y coordinate is -27. And that will be the coordinate on the line. Now, this coordinate connection only applies if it's f at a number or g at a number, whatever your function is. You're subbing in one x value into the function, and that's it. There's nothing surrounding it. But if you look at examples C and D, I have a coefficient outside of f at -2, or I'm subtracting f and g. So this doesn't represent a coordinate on either function anymore. This is more just an algebra skill. So for 3 times f at -2, this really just means figure out what f at -2 is and then triple that number. And there's different ways you can do this depending on what works best for you. If you would like, you can find f at -2 first, just do it on the side, and then do 3 times that number. Or you can do it all at once, which is what I'm going to do just to show you the proper way to write it out so you don't make a silly mistake. So I'm going to write the 3 outside, and then I'm going to open a giant square bracket just so I can differentiate between the 3 and my actual f at -2. And now I'm going to go to that quadratic and replace x with -2. So -2 squared plus 2 times -2 plus 4. And I'm going to clean up that f at -2 first. So I'm going to do all of this in the square bracket before I deal with that 3. That 3 is the last thing on my mind. So 3 stays there. And then negative 2 squared is positive 4. 2 times negative 2 is negative 4. And then the plus 4. And if we continue cleaning that up, 4 minus 4 is 0, plus 4 is 4. So f at negative 2 is equal to 4. So if you had done that on the side, you would get 4, and then you would do your 3 times 4, which is 12. And like I said, this doesn't represent a coordinate on your quadratic. The 4 does. That's the coordinate negative 2 comma 4 here, but the actual expression I wanted evaluated does not. Now let's try D, where we have f and g together. And again, you can do f at 2 first, do g at 3 next, and then subtract your values, or you can do them all at once. And again, I'm going to show you all at once just for the communication piece. And I'm just going to use the square brackets. Sometimes they're unnecessary, like you can use curved brackets, but I do it more to really separate the two pieces. So for f at 2, I will have 2 squared plus 2 times 2 plus 4 in one bracket, subtract, open another square bracket, and this time I'm plugging 3 into g. So that would be 5 times 3 minus 7. And I will simplify these two brackets independently, and that subtraction is the last thing I do. So for f at 2, 2 squared is 4, 2 times 2 is 4, and then the plus 4 at the end. And for my g at 3, 5 times 3 is 15, and then subtract 7. And again, I clean up each one individually. So 12 minus 8. And then I'll do my final subtraction here. 12 minus 8 is 4. And individually, this is f at 2, and the 8 is g at 3. So for all of these examples, I was giving you x, and you had to simplify for y, and then maybe do something else with it. But if we look at our last two examples, I'm giving you the y coordinate, and I'm asking you to find x. So for this first one, g of x equals 3. That means for that equation of 5x minus 7, I'm going to set it equal to 3. So 5x minus 7 equals 3. And now you have a linear equation you have to solve, meaning let's bring the negative 7 over, which means you actually add 7. So 5x equals 10. And then divide both sides by 5. This is now a grade 9 skill. So x equals 2. So that means you have the coordinate 2, 3. For the next one, f at x equals 4. So in that quadratic, I'm going to set the quadratic, which is x squared plus 2x plus 4, and I'm going to set it equal to 4. And now we have to remember our quadratic solving skills, which is when it is in the standard form, we have to bring everything over to one side. And when I bring that 4 over and I subtract 4, the 4's actually cancel out. So I'm left with x squared plus 2x equals 0. And the whole method of solving a quadratic equation is to solve by factoring. And the factoring method we would use here is just a simple common factor of x in this case. And now we can branch off and set each of our brackets, so x equals 0 and x plus 2 equals 0, and solve for x in each scenario. So this one is already done. X is equal to 0. But for the x plus 2, we have to bring the 2 over, and x is equal to negative 2. So for this one, we have two options, because when x is 0 or negative 2, y is equal to 4. So these are our two coordinates. And just because we have the same y's, it's okay because each x still only has one y, so this is still a function. Now let's get away from the algebraic method. You can also use function notation on a graph. So I have this graph here, the entire graph that's on there, that's f at x, and we have to evaluate a few things. Now you don't have to come up with an equation for anything, it's just very visual, and you have to understand what you're being asked for. So for the first one, I want f at negative 6. That means I'm going to go to negative 6 on my x-axis, and I'm going to find my relation. And here it is. When x is negative 6, y is equal to 1. For the next one, f at 5. So when x is equal to 5, I go to 5 right here. There's nothing looking up, so I go down And this is where I hit my function when y is -4. Now, f at -3. I go to -3 on my x-axis. I look up, there's my point. It's at 1. And I can do that for any value I want. And actually, I'm going to do one more for f at 3 because that one can be a little trickier. So let's just add f at 3 here. If I go to f at 3, 3 is right here. It seems like I have 3 options here, but the top one's a whole, the bottom one's a whole, so my only actual answer is that +3. F at 3 is 3. Now the last 4 examples are all you're given y, find x. So for f at x equals -1, I go to -1 on my y-axis and I try to find my function. There's nothing to the left, but I hit my function on the right when x equals 4. So x equals 4 would be my answer there. For f at x equals 4, I go to +4 on the y-axis, and this time I actually find my function to the right and left at -2 and +2. So I need to show both answers or else you're not fully correct. The next one, f at x equals 1, I go to 1 on my y-axis, and then on the right, there's one point right here that I'm going to estimate, but on the left, I have this whole line segment that is an option. So on the right side, x is equal to approximately maybe 3.25. We're just estimating, we don't know if it's exactly that. We can figure it out exactly if we wanted to by finding the equation of that line, but right now we're just kind of using the visual. And then we also have x is less than or equal to -3. That entire line segment is a potential answer, any point on that line. So there's an infinite number of solutions here. And finally, f at x equals 9. When I go to +9 on my y-axis, nothing to the left, and on the right side, there's a hole, which isn't actually a point. So for this last one, there is no solution. So for this last type of example with the graph, it's very visual, and you have to look at the entire thing to get all your possible answers and to not get tricked with holes or the closed points.